All right, I've been meaning to get to this for a while. I wanted to give some more involved examples of some error that you can follow all the way through your experiment and use them in an error analysis. So just to review, these are systematic errors that we're talking about because we want to predict the effect of the error. We want to say whether the error is going to push our results too high or too low. And if we have a random error, that's just an error coming from the precision of the instrument. So remember we were talking about the precision of an instrument. If this is the true value right here in the middle, a lot of those readings are going to be probably pretty close to that true value, and then you're going to have a few that maybe are too low and a few that are too high, but it's not going to get pushed in one direction or the other. So for example, if you are measuring a piece of paper with a ruler that has lines every 1 centimeter, and your paper width falls in between 13 and 14 centimeters, there's a line for 13 and a line for 14. Most people are probably going to read this as 13.3 centimeters. They're going to estimate that as a 3. Some people might estimate 13.2, and some people might estimate 13.4. There's no reason to think that the people who estimate it a little bit off are all going to be on the side of 13.4 rather than the side of 13.2. We'll probably get a little bit of each. If you have a systematic error, so the procedure itself or the way the student is doing the procedure is causing the results to be off in a certain direction. So for example, we talked about measuring diagonally across the paper. So a measurement taken along the edge of a paper versus a measurement taken on the diagonal, just the way triangles are, the diagonal is going to be longer. So the students who do it wrong, that is a reason to think that the students are all going to get a measurement that's too high, 13.4 or 13.5, because they're not measuring along the edge, they're measuring along a diagonal. So this is a systematic error. Just differences in the estimation would be a random error. It could be too high or too low. But doing it the wrong way, or doing it a certain way, this way, is going to make all of your measurements too high. So when we're predicting the effect, we're talking about systematic error. So here's an example from Lab 3, if you're doing the labs in the Chem 101 the way that I have them numbered. This is a lab where we're measuring the density of different salt solutions, sodium chloride solutions, that we made up in lab. And at the end of that lab, I ask you to consider a certain scenario. What if you used a volumetric pipette to transfer a volume of DI water and then did not rinse it with solution 1 before you used it to transfer the volume of solution 1? What would this do to the concentration of salt in the portion of solution 1 that you obtained the mass of? What would it do to the mass you obtained? What would it do to the density? Include whether each result you obtained would be changed in a positive or negative direction. Would it get bigger or smaller? So that is the question. And just in case you have not done Lab 3 recently, or you are not in my Chem 101 class and have not done Lab 3, let's review what that is. And what is done during that procedure is that we are getting the density of different solutions. DI water, solution 1, solution 2, solution 3, 4, and 5. So we have one volumetric pipette and we are using it to get to transfer 10 milliliters of solution into a weigh boat so that we can obtain the mass of that 10 milliliters of solution and get the density. So that's what we're going for in this lab. And so we are starting with DI water, using the volumetric pipette to transfer 10 milliliters of DI water into a weigh boat that has been tared or zeroed out on the balance, and getting the mass of that 10.00 milliliters of DI water eventually so we could get the density. And then what we're told to do is to take a little bit of solution 1 into that volumetric pipette and rinse it out. Don't fill it to 10 milliliters, but take a small amount in there, rotate the pipette, turn it sideways, coat the walls, and then discard this liquid into the waste container. So now the pipette, instead of being coated with DI water, is coated with solution 1. And now that pipette can be used to pipette 10.00 milliliters of solution 1 into your tared weigh boat to get the mass and eventually calculate the density. So this part of the procedure is measuring the mass of 10.00 milliliter of different solutions so that we can get the density. And in case you have not done the lab, solutions with greater salt concentrations are going to end up being more dense. So the lightest portion that we have is the 10.00 milliliters of DI water, and then as more and more salt is dissolved into these different solutions, it gets heavier and heavier because it's more and more dense. All right, let me see if I can represent what's happening here with the quite artistic drawings. So we have solution 1, let's say that it's about 4.70 mass percent sodium chloride in water, and you have a pipette that you just used for DI water. And so instead of being a clean, dry pipette, it has some water left in it. Maybe it's like some droplets of water. Let's be a little extreme in our example, and let's say that there is a whole milliliter of DI water left in your 10 milliliter volumetric pipette. Then when you draw up the solution into the pipette, it's mixing with the DI water. So when you draw it up to hit that 10 milliliter line, as you should, some people mistakenly think that they're going to go past that line, but there's no reason why you would go past the line. You're trying to do this the proper way. So let's say that you go up to the 10.00 milliliter line, but one of those milliliters is DI water and the other 9 are the solution 1, the 4.70 mass percent sodium chloride solution. So then when you put that 10.00 milliliters into your weigh boat, you still have 10.00 milliliters, but the concentration of that solution is less than 4.70% sodium chloride because it's been diluted with some DI water. In this case, an extreme amount, perhaps, of DI water. So let's compare the results that we would get from the error that was described. The correct procedure, you would draw up 10.00 milliliters, and the way the procedure is written, most people for solution 1 got slightly less than 5 mass percent sodium chloride in their solution 1. So let's say it was 4.70% sodium chloride. The density of something that's 4.7% sodium chloride should be about 1.032 grams per milliliter, and so if you have 10 milliliters of that, it should be about 10.32 grams. So in this exaggerated error where you had a full milliliter of DI water inside your pipette, you would draw up 9 milliliters of your 4.70 mass percent sodium chloride solution. If you do the dilution calculations on this, 9 milliliters of 4.70% salt diluted up to a total final volume of 10 milliliters gives you a concentration of 4.2% sodium chloride. So even if you don't try out this concentration using the dilution formula, you probably would see that when you mix 4.70% salt solution with water, you're going to lower the concentration of salt. You're going to make it more dilute. And because of that, you're going to make it less dense, because more concentrated salt solutions are more dense and less concentrated salt solutions are less dense. And I looked this up and it seems like 4.2% sodium chloride would have a slightly lower density, 1.028 instead of the 1.032 that you would have had. And so this difference is not huge, it is slightly noticeable. So when you put the 10 milliliters into your weigh boat, instead of weighing 10.32 grams, it's going to weigh 10.28 grams. So you would get a lower mass, a lower density. The concentration would in actuality be lower, although you would still probably be reporting it as 4.70% because you probably did not notice your mistake. If you did notice, you would have done it the correct way. So on your paper, you probably have written in your calculations that you have 4.70% in solution 1, when in actuality you had a lower concentration than that because you diluted it. All right, here is another example of a possible error that could happen in Lab 5, the hydrate lab. So one of the questions at the end of Lab 5 asks you about this possible error. What if a significant amount of hydrate splattered out of your crucible onto your bench while you were heating it? How would this affect your final molar ratio? Consider the effect it would have on each of the values you calculated in the calculation section, whether it would be an error in the positive or negative direction. So that is which things would be too big and which things would be too small in your calculations. So in case we have not done the hydrate lab, the procedure here is to put some hydrate into a crucible, which is a small ceramic looking cup, and obtain the mass of the hydrate that you are about to heat. And then we heat it dry, and that drives off the water. So the solid has water molecules inside the crystals, and when you heat it, then you drive off the water. It goes off as steam, as water vapor, and the compound, the solid that remains behind, is lighter. And we heat it several times just to make sure that all the water is gone, and then when the mass is no longer changing, we obtain a final mass. So we call this the final mass of the anhydrous salt. Anhydrous meaning it no longer has water molecules inside its crystal structure. The mass of the water is going to be calculated by subtraction because we do not capture the steam that is driven off. And so we cannot weigh it directly. Then in the calculation section, what happens is that the masses are converted to moles, both for the salt and for the water, and then the molar ratio is reported. We want to know how many moles of water are in the crystal structure of each mole of salt. So we report that as a ratio. That is the objective of this lab. All right, let's see if this drawing can help you visualize what's happening here. You have some solid in a crucible, and the lid is sort of tilted, slightly ajar, so that when you heat it, hopefully we're keeping the splatter inside the crucible, but there's some room for steam to escape because water, vapor, steam is going to escape from here. So we're starting with a solid that has water as part of the solid crystal structure. That's called a hydrate. Then when we heat it, the water goes away as steam. You get like got a little cloud here. So that's where the water is. And the anhydrous salt, the copper 2 sulfate, is left in here. What's left in your crucible is a solid. It does look a little bit different. It looks more powdery. It's a slightly different color, but it still is a solid. And the mass is less. There's less of it because the water was contributing to the mass, and now the water is gone. So we have a certain mass of hydrate, and then when we're done heating it, we have a lighter mass of solid, and we know that that is the anhydrous salt. So what we are saying happened in the error is that in the process of heating it, not just the water went away, but you also got some splatters of solid all over your bench. And so when you weigh the crucible, this stuff is not going to be calculated in that mass. So we are proposing that we lost some on the bench for the sake of being able to do calculations. Let's say that the amount that was lost and splattered onto your bench was 0.500 grams of substance. And so when people see the question, what happens if you splattered some of your hydrate onto the bench? A lot of people are just rushing through the lab report and they say, if I spilled some, that would make my mass too low, everything would be too low, my ratio would be too low, everything would be too low, I spilled something, I shouldn't have done that. And that is a response that does not show a lot of thinking about what really would happen in this scenario. I mean, it's definitely a good instinct and a good guess. Well, obviously, if you spill some, you have less and the numbers are lower. But that's not the case if you follow this all the way through. So let's compare the final results if you had done it correctly and not splattered any on your bench versus if you had splattered about 0.5 gram, so a significant amount, onto your bench. So in both cases, let's say that we start with 4.000 grams of the hydrate, and we're trying to use the hydrate copper 2 sulfate and see how much water is in there. That's why there's a blank there instead of a number, which turns out to be 5. It should be 5. So when you heat the water off, drive the water off of this copper 2 sulfate hydrate, what you end up with is 2.557 grams of just the copper 2 sulfate, the anhydrous salt. So this is just the copper 2 sulfate without any water next to it. The water that got driven off, by subtraction, you can deduce that 1.443 grams of water was driven off. then if you convert both of these masses to moles, 1.443 grams of water is 0.08010 moles of water. 2.557 grams of copper 2 sulfate is 0.01602 moles of copper 2 sulfate. And then if we calculate the ratio, moles of water to moles of copper 2 sulfate, we get that the molar ratio is 5. There's 5 times as many moles of water as there is copper 2 sulfate. So this is the correct answer, gotten with the correct procedure. If 0.5 grams splattered out onto your bench, then when you weigh the anhydrous salt, 0.5 grams are going to be missing. Instead of 2.557, you're going to get 2.057 grams of the anhydrous salt. So your amount of copper 2 sulfate that you report is going to be too low. You should have gotten 2.557 grams. Instead, you were reporting that you got 2.057 grams. When you do this subtraction, the amount of water that you say was lost is going to be too high. So you are thinking that the water got driven off when in fact just some stuff got spilled onto your bench. So this number is going to be too high. That's going to make the moles of water too high. You can see that it should have been 0.0801. Instead you get 0.1078 moles. So your moles of water are also too high. But your moles of copper 2 sulfate are too low. Again, because your mass of copper 2 sulfate was too low, your moles of copper 2 sulfate are going to be too low. When you calculate this ratio, you're doing it with a number in the numerator that is too high and a number in the denominator that is too low. And so the overall result is going to be fairly significantly high. So you're saying that you have 8.36 times as much water as you do copper 2 sulfate, which is definitely higher than the correct answer, which would be 5. So you can see that some of these numbers became too low, but other numbers became too high, including the final molar ratio. It ends up being too high. So your 3-second response, your instinct to say, oh, everything would just get too low, that does not turn out to be completely correct. So it does pay to follow the results all the way through the experiment, all the way through the calculations to figure out the true effects that you would see. And if it helps to make up numbers like this, then that is something that you can try. All right, so our third example, the last one that I'm going to go through in this video, is one from Lab 4, where you make a stock solution that contains copper 2 sulfate pentahydrate and cobalt 2 nitrate hexahydrate. You've got a very colorful blue compound, and then the cobalt compound is colorful red, and you're determining the concentration of these compounds by looking at the light, the colored light that gets absorbed by these very colorful solutions, and using a spectrometer. Okay, the question is, what if you had not rinsed all of your solid copper 2 sulfate pentahydrate into your volumetric flask for your stock solution? Would your reported values for the concentration of copper 2 sulfate pentahydrate in your tubes have been higher or lower than the actual values? How would this have affected the graph of absorbance versus molarity? Most importantly, how would it affect your reported result for the concentration of copper 2 sulfate pentahydrate in your unknown? Would you report a concentration that is higher or lower than what the concentration actually is? Okay, so let us go over the procedure for people who are not as familiar with Lab 4 and what we are doing here. So the procedure for Lab 4 involves weighing about 1.5 grams of copper 2 sulfate pentahydrate into a beaker and then transferring this into a 50.00 milliliter volumetric flask in order to make a stock solution with known concentration. That stock solution also has some cobalt 2 nitrate hexahydrate, so let's pretend you did the cobalt part correct, but the copper 2 sulfate is what we're worried about. Okay, so the stock solution, if you do it correctly, should end up with about 0.12 moles per liter copper 2 ions. If you used 1.500 grams of copper 2 sulfate pentahydrate, you would calculate your molarity as being 0.1201 moles per liter with copper 2 sulfate pentahydrate. Once you've made the stock solution, you make 5 test tubes with different dilutions of that stock solution. And the way that that's done is that tube 1 would get 1 milliliter of stock and 4 milliliters of water. So we're diluting all these volumes up to about 5 milliliters, and we're using a burette, so the readings do go 2 past the decimal, but we're diluting it from 1 milliliters to a total final volume of 5 milliliters. Tube 2 starts with 2 milliliters, then you add 3 milliliters of water to get a total volume of 5 milliliters. And then tube 3 gets 3 milliliters of stock, diluted up to 5 milliliters. So all of these are being diluted up to 5 milliliters using different amounts of stock solution. And so they all end up with slightly different concentrations of copper. And then we are measuring the absorbance of light close to 815 nanometers. In the procedure, you can pick which wavelength seems to be measuring the best absorbance of the copper. So you might come out with 810 nanometers, 820 nanometers. So we're measuring how much light is being absorbed. And that's proportional to the amount of copper that's in the solution. The more copper you have, the more light is going to be absorbed, the higher this absorbance value is going to be. All right, let's try to visualize what is happening here. So you have some copper 2-sulfate pentahydrate that you weighed out into a beaker, and what you're supposed to do next is to pour it into this 50 milliliter volumetric flask in order to make your stock solution. And so you can pour it through a funnel, and then if there's any left in your beaker, you're supposed to rinse it in with some water and get all that 1.500 grams into the flask so you can make your stock solution. So what we're saying happened is that you were rushed or not very observant, and so you left some behind in this beaker, and not all 1.500 grams made it into your volumetric flask to be dissolved in your stock solution. So how would that affect your experiment? For the sake of having a very exaggerated error and making it really clear to see what's going on, let's say that you were so rushed and careless that you only put half. So you only put 0.750 grams into your volumetric flask, and you left 0.750 grams left behind in your beaker. So that's kind of extreme. I doubt that would happen, but for the sake of the calculations, let's say that that did happen. All right, so let's compare the results of a fairly extreme error where you only added half of the copper 2-sulfate pentahydrate to your volumetric flask. And then for whatever reason, you got tired of pouring or rinsing the beaker, and so only half of it made it in there. The students who did the correct procedure have calculated 0.1201 moles per liter as their stock solution concentration. And then the types of dilution I described earlier, 1 milliliter being diluted up to 5, 2 milliliters being diluted up to 5, 3 milliliters being diluted up to 5, and so on, would end up with these concentration values of copper ions in your different tubes. Tube 5 is not diluted at all, so it's the same as the stock solution. And it's important to note that this is what you would report no matter what, because if you reported that you put 1.500 grams of copper 2-sulfate in your volumetric flask, if you did the calculations correctly, this is what you should have ended up with. If there was stuff left in your beaker, I don't see why you would have adjusted the calculations. You just would not have noticed that you left a bunch of stuff in your beaker, and I don't think any student would say, okay, well, I left half of this in my beaker, so let me cut all my numbers in half. They would just carelessly calculate this as if they had done everything correctly. So these would be the reported values, whether you did it correctly or not. So reporting these values but doing it incorrectly, your stock solution in reality would only have 0.06005 moles per liter of copper in it. Even though you calculated using the 1.5 grams, not all of it got in there. So in reality, your stock solution is more dilute. And in this extreme example, it's only half as much. And then all of your tube dilutions are also half what they should be. So since these concentrations in reality are half of what they should be, the spectrometer is not going to be fooled. If your tube 1 only has 0.012 moles per liter in it, it's only going to absorb half the light of a tube with 0.0240 molar. So the spectrometer is going by the amount of copper that is actually there. That's what's absorbing the light. And so this absorbance value, this student, tube 1, will get half of the absorbance that a student who had the correct tube 1 concentration would get. So all the absorbances would be half of what they would have been if you had done the correct procedure, and half of what the students who did do the correct procedure are getting. Your values are going to be half that high. Let's take a look at what it would do to the graph if all of the absorbances were cut in half. So I don't have the true absorbance values for these solutions. I just made up some numbers and then I cut them in half for the solution that was made in error. So for both of these solutions, our reported concentration values, 0.024, 0.0480, these molarities are the same for both of these lines. So the blue line is the correct line, and this is the line if you made that error and only had half of the copper in there. So the stock solution should be absorbing at this level. If you only have half the copper in there, it's going to absorb at half that level. So this is the absorbance you would see for the solution that you made in error. And all of these values are cut in half as well, which would give you a different line equation. However, it would not affect the quality of your line. So if you did the dilutions the correct way, if the only error you made was how much copper is in your stock solution, but you diluted them the correct way, then you should get a nice, consistent, straight line anyway. That's not going to be the problem with your graph. The problem is that the line is going to be, the values, the y values, the absorbances are going to be a lot lower. So the slope is going to be lower in your line, and your line is going to be lower than it should have been. So how would this affect your unknown solution? So let's say you have an unknown solution that has an absorbance around here. So this is your unknown. And you can try this by plugging in a certain value for y into these two line equations and see that your x value would come out higher in the erroneous line than it would in the correct line. But let's take a look visually at the graph. So if your unknown had an absorbance around here, then what plugging it into the equation actually does is find the point on that line and find the corresponding x value. So that's what you're doing algebraically when you plug that absorbance value in for y. You're going to get a certain x value over here. So this is what would happen if you had the correct line. The blue line is the correct line. So you would get an unknown with this absorbance value, you would plug it into the correct line equation, and you would get an x value of 0.040 molar as your unknown concentration, and that would be correct. If instead you had this erroneous line and you did not have this blue line, then when you put in your unknown, your line would have this as the x value that matches that y value. So you're going to be reporting this x value as a higher value, and since we've halved all these absorbances, it should come out double. And you can do the same thing algebraically by plugging in a certain y value to this equation. You will get an x value that is higher because you're going to end up dividing y by a smaller slope than with this equation. But in any event, you're going to be reporting an unknown concentration that is too high. Even though because all of your absorbance values are too low, then that's what happens when you report your unknown concentration. It's going to come out to be too high. So what would this do to your unknown concentration? Well, you are using the lab to determine your unknown concentration. So let's say that your unknown that you were given happens to be 0.0480 molar in copper ions. So what would you report? Well, if you had done the procedure the correct way, your absorbance for your unknown would happen to match tube 2. And tube 2 has 0.0480 molar, and so your unknown value would fall onto the line right next to the dot, or right on top of the dot for tube 2, and you would report the correct value as 0.0480 molar. If you had made your solutions the wrong way, 0.0480 molar is the amount of concentration that tube 4 has. And so your unknown would match the absorbance results that you got for your tube 4. And so it would fall on the dot that the tube 4 is on your graph. And so you would report it as matching tube 4, which you say is 0.0961 moles per liter. So your reported value would be twice as high as it should be. You would be reporting 0.0961 because that's what you believe tube 4 has in it. Unfortunately, your tube 4 actually has 0.0480 molar. So you're ending up reporting a value for your unknown that is too high, twice as high as it should be. So even though it seems like some of the, your 3-second reaction would be like, okay, well, if I left my copper behind, the concentration would be too low, the absorbance would be too low, and I would report a value that's too low for my unknown. And in truth, you would be reporting a value that's too high for your unknown. So that's takes a little bit more thought and a little bit more analysis to come up with that answer. All right, so some final advice for doing error analysis is to really try and think about what you're doing and picture your procedure, picture what the error described would do to your procedure. If you are coming up with your own error, a lot further on in the semester, I have you come up with your own error, or other professors might have you come up with your own errors. Try to imagine the error occurring. Imagine what parts of the lab might have given you some trouble, what you might have done wrong if you had not been as careful, perhaps what you saw some of the other students around you doing wrong if you were in lab with some students who seemed to be confused. So try to picture what that error was and try to visualize what that would do to your measurements or to the results that you're getting from your lab experiment. And then if it helps you to use an actual number, you can even do something that's really extreme, saying, okay, well, this number would be too big. What if I actually doubled it? Or our last example, what if I only got half of my copper? So that's a really big change. Sometimes it's easier to follow a change in your calculations if it's really, really big or really, really small, and then you can see much more clearly what it's doing to your calculations. And make sure you follow it all the way through, because sometimes a measurement that's too big causes a final result that's too small, or a measurement that's too small can cause a final result that's too big. So you do need to follow it all the way through the calculations and the experiment and see what the final result would be.